This chapter, we are going to study numerical simulation of optimal jump. Again, for your as a reminder, the hypothesis was there are optimal speed and angle exist for long jump and high jump because based on the observation, there are two different strategies for high jumps and long jump. So we are wondering, can our mechanical analysis with the muscle activation could provide any explanation for this difference? So for optimal solution, so for two input variables like a combination for theta and v naught, maybe there are some global maximum exists that will give us maximum height or distance performance. So that's the optimal point. Or we may have some monotonic increase or decrease of the performance as a function of input variable theta and v naught. So what that means is maybe you do better run faster to get further, or you have a steeper angle to get higher jumps. So whatever we have, we will be able to interpret our simulation results in terms of physics and actual human data. One MATLAB tip for calculating this mesh grid is you can either actually you have to store the value for the distance performance measure as a function of theta and v combination, right? So maybe you could have two for loops for that, or you can just define it as a variable as a mesh grid. That means you have a combinations for all the variance for the x-axis and y-axis, and just plug in those mesh grid defined variable as a function to calculate the performance. Just as a little tip for your MATLAB. Okay, so for your MATLAB code, it's gonna be main code that actually have some definition for the parameters in the very beginning. Parameters, and if necessary you can use the global setting, and since you're scanning as a function of two input variables such as v naught and theta naught, you have to first define the range that you would like to scan through the simulation. Then since you have a two inputs, you will have a two for loops, right? If you have a three input variables, you will have a three for loops, okay? So for that for loops, you should set up the what's gonna be the corresponding initial conditions for that iteration procedures. And then with that initial condition here, you have to calculate the dynamics, the equations of motion for the jump. And when you actually stop integration at the takeoff, with those takeoff variable, you can find out what's gonna be the height and distance with that, and you just store them. So later at the end of the for loops, you will have matrix has a height information and distance information corresponding specific velocity and theta naught. For your sub function, the f underscore jump, you will have a solution for the equations of motion. So here the different thing compared to our previous coding is now it's active motion, not a passive one. So you have to define the force, external force applied. So luckily those muscle force are formulated, we assumed, as a form of a state variable x. So join angle here. So state variable x will give us the information what will be the angle for the phi, and with the phi dot information we will obtain the magnitude of the joint torques, and joint torques has a relationship with the ground reaction force as massless leg and point mass assumption. So with that external force specified, you can implement this to calculate the acceleration. Okay, so that's the actually solving the equations of motion part. Okay, without any event to occur, you just keep integrating it. Okay, so your value is going to be returning the acceleration vector, and whenever there is an event occurs, means takeoff occurs, either torque is going to be 0 or legs has been fully straightened, then you will stop integration. So I's terminal is going to be 1. Direction doesn't matter. It turns out to be 0. So your value is going to be 0 when either torque equals to be 0 or legs are been straightened up. So I just multiply by t and sine phi over 2 as a value. So by doing so, you will have a whole variable resultant variable for the height and distance, and we'll see how it look like. Okay, so first let's examine the high jump. So as a function of two input variable here, v naught and theta naught, you will have a contour plot here. So it seems like there's a local global local maximum exists here, right? So at this maybe somewhere in the middle, that may be the optimal point. So as you draw a line, even though you are at the same speed, by having the stiffer angle, you will gain the height at some point and you will reduce the height. So increase the theta doesn't really gain much because at certain range you increase the height, at a certain range you reduce the height. However, for the velocity has a specific preferred range here. So somewhat in the mid-range run-up speed gives the higher jump. Okay, so your optimal simulation results can be compared with the human data, and surprisingly, I mean, very simple model could match the data very well. So your optimized velocity turns out to be 6.6, which is pretty much similar to the data. Same for the angle, and the takeoff angle, or maybe it's a takeoff theta, I guess. Takeoff theta may be a little bit different, but your reachable performance, the maximum performance for the height, sorry about that, height, it's are pretty similar, right? So once you're succeeded, even validate your hypothesis and matching the data, you must be really excited. And at the same time, you should actually doubt yourself, like doubt your procedures, like maybe your assumptions luckily match it, worked well, and then give you the really nice result. So that's why you have to perform the parameter study. So is your change for the parameter very sensitively affect your end results? That's what you have to examine. So maybe our assumption for T naught may be too customized. So maybe different maximum torques or ignorance of the tendon might change the results, right? So that's what we could do with the parameter study. And those parameter change show that different absolute value for the height. However, optimality, existence optimality is what we hypothesized in the very beginning, right? So that still holds. Okay, so the mid-range velocity and certain range of angle gave us the maximum height. So even though the leg configuration has been slightly changed, those optimality hold. So what that means is our approach of the point mass and force velocity dominant approach is still hold regardless of the parameter changes. Okay, let's examine how about the long jump results. So as a function of two input variables, that's velocity and the theta, this is the long jump result. So as you can see here, for the theta, if you goes up, so maybe you have a little bit more increase for the distance, and for the speed wise, faster the better. Okay, faster the longer. Okay, which makes sense. So different from the high jump, the horizontal takeoff velocity is a lot more important for the long jumps. So I mean, the faster speed is preferred, and for the angle, it's beneficial. You have a higher angle slightly, like those changes for the theta as the change of the theta to the effect of change of theta to the distance is a lot less than less compared to the high jump. And your results, the optimized results for the maximum long jump, it turns out to be pretty much similar speed and the angle. Again, that's gonna be maybe the theta here. Pretty much similar to the data, surprisingly, right? So with that, I mean, it's happy having such a feasible results using, even though you're using really simple model, then you should have to also ask yourself why it's such a simple model, even though I change the muscle parameters, sort of a lot, doesn't really affect the final results. So I would interpret that as maybe that's because the mechanical dominance in jump dynamics. What I mean is mechanical dominance is your run up and the take up happens really short amount of time, right? So there are not too much room for your control action contribute the performance changes, right? So even though your muscle also, of course, should generate the forces, variability of that control couldn't contribute much compared to your own dynamics. Your initial velocity and your mass, your height would actually will determine the results. So that's what I mean by mechanics dominance. So if we have more time dependent motion, maybe the controls role will kick in more important. Okay, so once we have all those simulations and the results are obtained, that's what I want to say, what I want to emphasize, that you have to check your answer and how feasible your results are compared to the human data or mechanics perspectives, and also you should verify your previously set assumption of holds. So for example, you assume the force velocity will dominate the results, but what if you also include the force length and etc. That's kind of that's a good example for you have to go through when you're doing the human motion analysis study. Okay, let's do an interpretation for the results in terms of impulse momentum perspective. Okay, so your momentum has changed by as a result of applied impulse, right? And then during those short period of stance for the long jump and high jump, the goal is you have to, change your momentum, right? Momentum upward for the high jump and forward for the long jump. So the only way you can get an impulse is from the ground reaction force by actually pushing out the ground by actuating the joint muscles. So you want the minimum impulse changes for the long jump. You don't want to lose the momentum, right? So usually the contact force are against your forward motion. You want minimal impulse. As opposed to that, you want larger momentum change required because you have to go up. Since you're running to the horizontal and you have to change your momentum into vertical, so you have a large amount of impulse required. So compared to that, the impulse is that the time integral of your force over time. To have a greater impulse, that means either force should be really large or the T will be large, right? However, those forces are as a function of your muscle forces because it's depending on how hard you push the ground. That is as a reaction, ground reaction forces are applied to your body. So the muscle force magnitudes are pretty much limited in its range because it's all dependent on the muscle properties. As opposed to that, those force contact duration could be doubled or tripled based on your action, right? So that's the main role that'll contribute to determine the magnitude of the impulse. And also, to obtain the upward momentum, you have to exert the force downward as a reaction so that the ground reaction force applied upward. So combine those two. If you are really in a very fast run-up speed, that will decrease the contact time. You will have a really small impulse applied for that. That means you have little change for the vertical motion, and then you don't lose a lot for your horizontal momentum. However, if you have a somewhat moderate speed and then you have increase your ground contact time, that means you have a greater impulse, like a opposite direction and up. So that'll help you to gain the greater impulse in the vertical way and then greater reduce for the horizontal direction. So that's going to be beneficial for the high jump, and this is going to be beneficial for the long jump. So pretty much makes sense in impulse momentum perspective. To summarize, we examined the optimal jump strategy using a very simple point mass mechanics combined with the muscle dynamics, pretty much about force-velocity relationship. So high jumps, you want the vertical component more important, as I said before. So you want to have a more ground contact time, and then sort of somewhat slow or a moderate runner-up speed. As opposed to that, for the long jump, horizontal components really matter. So you want to minimize the contact time so that you run real hard, fast, and run up, and stiffer touchdown angle. So pretty much makes sense in terms of physical interpretation wise. So we examined the simple example for the jumps, and next time we are going to study about the throwing.